All right, now let's go into some examples. Which of these statements accurately applies the law of large numbers? Remember, the law of large numbers, we're looking at the fit between our data and the real world. Does it really predict or look like the real world? An opinion pollster says, all I need to do is to ensure the accuracy of the poll results is to make sure I have a large sample. That sounds reasonable because we want to make sure that our poll results, so if we say, who do you think will win in the next election, we want to make sure that that matches, the actual population of voters. If you have a really large sample, that's more likely going to match the real world. A casino so this one, yes. A casino operator says, all I need to do to ensure that the house will win most of the time is to keep a large number of people coming to my casino. Let's think about this one. So the law of large numbers is about having a lot of data. Then whatever your data says, you know that will probably match the real world. Well, the house winning, those are probabilities that are set by the games, right? However the games are set up. Will having a large number of people coming in affect those probabilities? No. You'll probably just have to change those probabilities first, right? So this one is a no. No, the number of people coming in aren't going to help change those probabilities to help you help the house win more. That's not going to change the probability. So the law of large numbers doesn't say that having more data will change the probabilities. It just says having more data will help you know what the real world probabilities are, right? So it just helps you understand. It doesn't help you change the real world. A manufacturer says, all I need to do to keep my proportion of defective light bulbs low is to manufacture a lot of light bulbs. Well, this is a faulty understanding of proportion, right? Proportion is, percentage, right? And that's relative. So if you have a really crappy factory and let's say 25% of the bulbs are defective, right? Whether you have a small number of bulbs or a large number of bulbs, it'll still be 25% that are defective, right? So if we have a lot of bulbs, that's not going to change the proportion. So once again, it's wrong because the law of large numbers doesn't help you change the real world probabilities. It only helps you understand them or know what they are. So example 2, suppose you flip a fair coin 7 times. How many possible outcomes are there? So thankfully it doesn't say list all of them, just says how many possible outcomes. So think of each coin flip as a slot where one of 2 things can happen, heads or tails, 1, 2, 3, 4, 5, 6, 7, okay? And there are 2 possibilities for each of these, right? So 2 to the power 7, right? That's your answer. Suppose you roll dice 9 times. How many possible outcomes are there? Well, 2, 3. So it's sort of like think of each roll of the die as a potential event that could have 6 different possibilities, right? And so each has 6. And so this would be 6 to the 9th power, right? And so the other way that you'll see the fundamental rule of counting is that it'll usually say, oh, if you have n events, so events are the little possibilities. So if you have n possibilities, and k number of events, then total outcome is something like n to the k power, right? And so here, you could see, if you have n possibilities, so 6 possibilities for each of k events, then it's 6 to the ninth. And same thing here. I may have mixed up the n and the k. I always forget which is which. But, this is roughly that idea, right? And you could see it more readily when you see each event as sort of a slot to be filled with some possibility. All right, example 3. Suppose 5 taste testers are comparing 3 brands of coffee. What is the sample? What is all possible outcomes? So here, maybe they taste one coffee and they have to pick whether it's Starbucks, McDonald's, or Dunkin' Donuts. This question is actually a little bit poorly worded because it's a little bit vague. But let's say that that's what this question is asking, right? So, so what is the sample? What's all the possible outcomes? So what might these people guess, right? So if I have 5 taste testers, and each of them can have 1 out of 3 guesses, right? So Starbucks, McDonald's, or Dunkin' Donuts. So that's 3. That's 3 to the 5th power, right? And what you want to do is make sure that, all the sample space is covered. So the 5 taste testers, the first one, you want to have the equal probability of the first one picking Starbucks, the second one picking Starbucks, the third one picking Starbucks, McDonald's, Dunkin' Donuts, and so on and so forth, right? And so it might be helpful to figure out what this actually is. So it's like 9 times 9 times 3, so that's 81 times 3, so that's about 24. Oh, that's a lot of possible outcomes. So I would say, why don't we leave it at that and not draw it out, right? So that's a lot of possible outcomes. If it's that big, usually they won't ask you to draw it all out. I think that the biggest I've been asked to do is like 32 possible outcomes. All right, example 4. A study of different treatments for anxiety randomly assigns each newly diagnosed patient to one of 2 levels of exercise, mild or moderate, and one of 5 different types of medication. How many different treatments are there? Show the sample space as a tree diagram and as a table. Okay. So first thing is, how many different treatments are there? Well, the first slot will be levels of exercise. They get one of 2 levels of exercise. But the second slot is 5 different types of medication. And we'll just call these, A, B, C, D, E, right? Those are the 5 different kinds. So there's 10 different treatments. Well, let's get started. So first, we'll have the exercise, and then we'll have the medication part of the tree. So the exercise part of the tree will be, mild and moderate. Medication will be A, B, C, D, E. A, B, C, D, E. Okay, great. And so if we looked at all the outcomes as sort of a table, we could look at it as mild, 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 with A, B, C, D, E. Same principle as before. Mod, 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 mod. Moderate exercise with A, B, C, D, and E. And each of these different treatments are equally likely, or we want it to be equally likely in our sample. So just to zoom in a bit, for instance, if we look at this, this treatment group, this group of people or group of experimental cases gets assigned to mild exercise, but also gets medication B, right? All right, so that's the end of sample spaces.